know. All right. So my name is Bartosz Rabiega, and I have this great opportunity to talk to you this morning. And I would like to tell you a story today, how we at OVHCloud have implemented an NVMe over Fabric storage for our public cloud services. Who am I? I've been working for OVH since nearly 10 years, since 2016. I think for the whole time I've been part of the block storage team. I've been a DevOps engineer there. Currently I'm a technical leader. So I'm a Python developer. I do a lot of automation in Puppet, and I'm also a set administrator. And I do some development of OpenStack when it comes to Cinder and Nova. So OVHCloud, since we are in France, then maybe the company doesn't need a big introduction here, but still I will say a couple of words. We are one of the biggest European cloud providers right now. The company was founded in 1999. The whole story started with the bare metal servers and some hosting services provided for our customers. About 2015, we have started our public cloud offer, which is based on the OpenStack technology up to this day. We have about 40 data centers located all over the world, and we have about 40 production-grade OpenStack deployments worldwide, variety of sizes. So, just to give you some context about the block storage at OVHCloud, we currently run most of our infrastructure based on Ceph technology. It's an open source project which provides the software defined storage. It's really well integrated into the OpenStack world, and it's very widely used in the industry right now. So a few words about the scale. We are currently running about 430 Ceph clusters, and my team is responsible for daily care of those clusters. 260 from them are dedicated for the public cloud services for the block storage. So my team is basically doing a Ceph as a service. When someone needs storage, he can come to us and we deliver Ceph clusters. We take care of them, we do the maintenance, we replace the hardware, the disks which are broken and stuff like that. And the users can just consume that. So we also have a Ceph for the external customers. It's called Cloud Disk Array. So anyone can buy such a Ceph cluster and consume it. From the top level point of view, we have multiple OpenStack regions. Each OpenStack region has a Cinder, which is responsible for the block storage services. And each Cinder has multiple backends configured, and each backend corresponds to a single Ceph cluster. So you may ask yourself a question: why do we need multiple Ceph clusters per single OpenStack region? Well, the answer is that we want to limit the blast radius when something is wrong in case of Ceph cluster. Things happen, sometimes bad things happen when we, for example, upgrade clusters. Sometimes we have some hardware problems. So we want to avoid the unavailability of the whole OpenStack region at all costs. We want to avoid. Okay. So since we are using Ceph so widely, there's a question: why do we need another kind of storage? Why do we need NVMe over Fabrics? So NVMe over Fabrics comes with a promise of bringing an ultimate speed to the block storage world. It is supposed to bring a low latency and predictable performance, but also it promises to bring a significantly simpler data path comparing to Ceph, because Ceph client is pretty intensive when it comes to the CPU. It needs to do a lot of calculations to do the I/O. Also, I mentioned that Ceph is very widely used, but it's not an industry standard, while when it comes to NVMe over Fabrics, it is an industry standard right now. There are big technological companies behind it, like Intel and so on. Also, what is interesting is that it has a native support in Linux kernel and and other operating systems. Also, it is possible to attach NVMe over Fabrics devices at UEFI level. at least theoretically. I didn't do it in practice, but it is possible. And also the Mellanox Smart NICs, which NVIDIA is producing right now, are able to run NVMe over fabrics in the hardware. That's really nice. Also, it was a buzzword between 2016 and 2020, but I guess nobody would be taking any serious decision based on a buzzword and hype, right?
It never happened.
Yeah, it never happens. Yeah, right. Fortunately, this isn't only a buzzword, so some of the promises are delivered by NVMe over fabrics. So, in the 2020, OVH has acquired a USA-based startup called Extend Technologies. And the startup was basically building a software-defined storage similar to Ceph, but with NVMe over Fabrics access. So it provides HA capabilities, just like Ceph. It provides the high performance with erasure coding. When it comes to Ceph, the erasure coding is also possible, but the performance is a little bit not as you would expect from the hardware you have. So the first production cluster we deployed was in 2023. At the moment, in our production systems, we run about 10 Extend clusters powering the block storage services for public cloud. From the top level point of view, not much has changed. As we have multiple backends for Cinder, we have another backend which basically is Extend. And in the future, we're going to put more Extend clusters as backends, and maybe we will remove some Ceph. We will see how it goes. If you're interested about the performance numbers, I have performance numbers for a single volume. So for example, with Ceph, you're able to reach like 25,000 IOPS, 4K IOPS random, with single volume and single IO thread. With the NVMe over Fabrics we currently have, we have about 50,000 IOPS with erasure coding, while for Ceph it's with free replica. So this is the difference we currently have. And there's a lot of room to improve here. We'll see in the future. Okay, so just to give you some technical overview of the NVMe over Fabrics. What are the requirements to connect NVMe over Fabrics device? They are pretty low, I would say. You need some not so fresh Linux kernel, 5 point something, and that series supports NVMe over Fabrics with native multipathing. This is something which we need to have HA capabilities. We need a kernel module and NVMe TCP to run NVMe over TCP. And we need NVMe CLI tools, which is a Linux package with a set of tools to interact with the kernel to, for example, connect the NVMe device or link them or disconnect, stuff like that. So what do you need to connect NVMe device if you have all the requirements fulfilled? You basically do NVMe connect and pass some parameters like an IP address of the storage target and 2 identifiers in our case. It's a subsystem NQN. So subsystem NQN is like a volume identifier in NVMe over Fabrics. And another one is a host NQN. It's another unique identifier. In case of our storage, we need both of them to connect the NVMe device. Once it's connected, it's present in the operating system as a typical block device in /dev/NVMe number something. This is how it looks. So, NVMe comes with 2 operational modes. One of them is the standard TCP mode. It can work on pretty much any hardware. And the secondary mode is RDMA. Now, RDMA is a little bit more interesting because in order for it to work, you need a special configuration in your switches. Basically, the entire network path between the initiator and the connector needs to have the PFC technology enabled at switches. It's a flow control for the packet flow control or something like prioritized packet flow control, something like that. So basically it allows to prioritize the RDMA traffic and so to have the stable connection and to maximize the performance. Now what are the benefits of RDMA? It has a minimal protocol overhead because it uses UDP packets compared to TCP. So it can have much better latency and much better performance overall. In the document, they say it's twice to 10 times faster comparing to TCP. However, I have to say that at the moment at OVH we're using the standard TCP mode. In the future we will probably switch to RDMA, but it will take some time to prepare the whole infra for RDMA. Another feature which is essential for the cloud providers is the high availability features. So NVMe comes with native multipathing. It works pretty simple when you attach multiple NVMe devices to a Linux kernel. When those devices have the same serial, the same disk serial, Linux kernel will treat them as the same block device, and it will basically expose single block device with multiple data paths. It works in like active passive mode. When one of the data paths is gone, all the traffic will go through the second data path, and in the background, Linux kernel will try to reconnect that missing path. Once it's established, you have HA once again. This is very important when you, for example, want to upgrade some nodes, some targets, or whatever. So, kernel comes with the native support for that. Okay, so we have a storage system, but we need to somehow integrate it into the OpenStack world. So, what do we need? We need to modify two basic components of OpenStack. One of them is Cinder, and the second one is Nova. Cinder is responsible for the management part of the volumes. Basically, it creates volumes. Here it is. These are the basic functionalities of Cinder driver. It creates and deletes volumes. It creates snapshots. It's also responsible for some advanced features like creating a volume from volume, or a volume from image, and stuff like that. So in our case, we have developed a volume driver. The OpenStack Cinder is pretty well designed, so you can just add additional piece of Python code. It's called the volume driver, and it is responsible for translating Cinder requests to your storage API requests. In our case, we have a RESTful API in our Extends cluster. So it was pretty easy to implement. The only thing we needed to add is some kind of a HA layer, because when one of the RESTful API node is down, for example during the upgrade, you still need to handle your customers to create volumes and basically manage them. That's what you need. On the other hand, you need something which is called Nova connector, and this part is responsible for the attachments. So for example, when the customer wants to attach his volume to the virtual machine, it's the Nova and the connector code. They are responsible to expose the volume inside the virtual machine. So fortunately, we didn't have to write this part of the code because it's already in the OpenStack upstream code. Unfortunately, in 2022, only single path NVMe over fabrics were supported by the OpenStack upstream code. Native multipathing was on its way. And during that time, we were already trying to implement it for our production systems. So we kind of had a problem because this was implemented, the native multipath support was implemented in 2022 in the upstream, but our production were running on a still slightly outdated version of OpenStack. So either I had to backport the new code for the old code, and I had some problems with that, or maybe do something else. So at that time, I realized that nearly 50% of the Cinder of the connector code is responsible for doing like local replication. Before the native multipathing was available, basically the connector was setting up a local write on the compute host and attached multiple NVMe devices. So this is something we completely don't need if we use native multipathing. And I had a problem with backporting that code because I would have to test everything. I don't know how to test it, so I took the lazy approach, I have to admit it. I just took all the code that was responsible for the native multipathing, and we created a new connector that is compatible with the upstream connector, with just the pieces of code which we need. The idea was to, in the future, once we upgrade our whole infra, we will be able to switch to the upstream connector, and that's it. So this is actually what happened. We have implemented our in-house connector, which is compatible with the upstream connector, and it only supports the native multipathing to satisfy our needs. And we made it as simple as possible to make it bulletproof to run it on production. So we have all the required pieces. We have Cinder driver, we have the Nova connector, we glue it together, and at this point we have NVMe over Fabric support in our OpenStack deployment. At this moment it's possible to do OpenStack volume create, it will be created on the new storage, and it's possible to attach the volume to a virtual machine. Through the connector it will be attached. But there's something we are missing here, because we didn't realize that the architecture of volume attachment on the compute side has changed significantly comparing to Ceph. Let's take a look. This is an example how the Ceph attached volume works. So in case of Ceph, there's a library called librd, it's a part of Ceph. And it's responsible for basically all the stuff related to connecting to Ceph cluster, doing the IOs, but also keeping the connections alive and making it HA. librd is loaded by QEMU process, and basically this is how it works. It works in the user space. So all the IOs, all the connections, all the HA, it's handled by the user space. And this is significantly different comparing to the NVMe over Fabrics, because NVMe device is connected at the hypervisor kernel level. So it's the hypervisor kernel which handles the I/O, it handles the HA, it handles all the connection stuff and all that thing. The only thing that QEMU does, it consumes the NVMe device from the hypervisor and exposes it as a volume, as a virtual disk inside the virtual machine. So this part is entirely in the kernel space. And there are some bizarre effects of such a change that you need to take under consideration. For example, let's take a look what happens on the compute side when someone wants to attach an NVMe device. First of all, the request goes to Nova, to the Nova agent which is running on the compute side. And that Nova agent uses the connector code to connect the NVMe device at the hypervisor level. It basically does the NVMe connect command with the parameters given from Cinder. So let's say we do NVMe connect with the NQM XYZ and some IP. Okay, that's cool. What happens next? The problem here is that the tools for the NVMe don't know what kind of a device name will be assigned by the kernel to the NVMe device. So the code inside the connector, inside Nova, needs to scan sysfs in Linux to find the appropriate device that was just connected. So it scans all the sysfs block devices to find the NVMe device with the matching NQN number. And if you remember, the NQN is a unique and the identifier of the volume. So that's how it works. Once it obtains the correct NVMe device, it gets its kernel-based path, like /dev/NVMe5 and 1, and it passes it to the libvirt. Then libvirt instructs QEMU to consume that device and expose it as a virtual disk. Okay, fine. But we need to take a look how the kernel assigns the device names, because it's kind of a tricky. Let's take an example. When you connect NVMe A, it will get like /dev/NVMe5. When you connect NVMe B, it will get the next sequence number available by the kernel. So it will be NVMe 6 and 1. But if you disconnect NVMe A, the NVMe 5 will be released. And then if you connect NVMe C, it will get the same name as the volume A previously had, the NVMe 5. Now this is a little bit tricky, maybe concerning, especially if you take a look how the whole flow of the attachment works. especially when the red bar is present on the chart after the connector scans for the block device on the sysfs. If you manage to do something stupid here, like disconnecting volume A and connecting volume B, it will reuse the device path that was previously used by the volume A. And effectively, you will be able to attach, by mistake, volume B to the VM instead of volume A. So OpenStack does everything it can to prevent that. It's doing some locks and stuff like that. But still, this is a little bit concerning, at least to me. So we've been thinking what to do with that. And since we have our own connector, maybe there's a way to improve this situation a little bit. And there is a mechanism in Linux kernel, it's called UDEF rules. And UDEF rules are basically the scripts that are processed when the new device is attached to the kernel. And at the time when UDEF runs, the kernel exposes some device attributes. And one of those attributes is the NQN identifier of the volume. And as I said, the NQN is unique per volume. So maybe we can make the device name predictable and not reusable by leveraging the NQN number attribute, the NQN attribute exposed by kernel. And this is exactly what we did. We are basically renaming the NVMe devices to NVMe-NQN. This is not reusable, this is completely unique, and this solves all the problem I mentioned earlier. But also what happens is that nearly half of the code of the connector is gone, because you no longer have to scan the sysfs for the device. You just wait for the device path to appear in the system, because you know what the device path will be before even doing the connection. And this is what runs on our production right now, since 2023. And there are no problems with that at all. The second thing, funny thing maybe, I don't know, is that when you connect NVMe over Fabrics, it's exposed as /dev/NVMe device, like an ordinary block device in your system. And you can imagine that sometimes some operator has to come and maybe fix your system for some reason. And maybe he will do like an KFS on the wrong NVMe. So this is also a little bit scary. So yeah, again, we used user tools to just move the NVMe devices to a different location. So we move all the volumes, the NVMe corresponding to volumes, to a different location. That's how the operator will not make a mistake. Still, if he's insane, he will do some harm, but let's just think that we are all sane. Another funny thing is that, for example, when the customer sets up an MD write on his volume inside the virtual machine, it will be visible on the at the hypervisor level. Because again, all the UDEF rules on the hypervisor are processed there. So it scans when the device is attached, it scans it. If it detects the MD write, it tries to assemble it. But come on, it's the customer's data, we can't do that. So we did, again, we modified the UDEF rules. We apply our two UDEF rules to mangle with the names and the location, but we disable all the UDEF rules that are present and could interact with the device from the hypervisor level. That's it. This also runs on our production, and it prevents some stupid things. Okay, one more thing. About the user space and the kernel space. So for example, when the QEMU process dies for some reason, I don't know, whatever reason. If it dies, in case of Ceph, it kills the librd because it lives in the QEMU space. So the whole user space is dead, and the connection to Ceph cluster is gone. There's no volume at hypervisor level. But when with NVMe, it's completely different. When the user space is dead, the kernel part is still present, and the NVMe device is present in the system. So this is something you need to take care of, because it's possible. We don't kill our virtual machines by killing QEMU, so I don't think we observe that on our production, but still it is possible. All right, but we do observe some things on our production. So for example, when you upgrade one of the backend nodes, it is possible that the kernel will connect only, because in typical situation, we connect 3 data paths per single NVMe device. But when we, for example, upgrade one of the data paths, we upgrade one of the storage servers, the kernel will not be able to connect one of the devices when the customer attaches the VM, when the initial connection is done. And if it cannot establish the initial connection, it will not remember that it is supposed to have 3 data paths. So it will remember only about the 2 data paths. So we do monitor for that situation. It happens very rarely, but we need to manually recover from such a situation by manually attaching the 3rd data path. And during the time in 2022 when the development of the native multipathing was in the upstream of the Cinder and Nova, there was a discussion. I did participate in that to allow some custom NVMe over Fabrics agents, because this problem will be basically present for all the custom software-defined storage that the users may have. So the idea was to run some NVMe over Fabrics agent on the compute side that will recover from such situations. Another problem is when you want to replace your storage server with a storage server with different IP. Also, nothing will replace that. In case of Ceph, it's completely transparent. Ceph does that for you. Now, nothing will do it, and you need to somehow fix it. And there are also some weird race conditions sometimes in OpenStack. I'm not sure if they are still present in the upstream. We will probably check it. Very rarely it happens that the volume is deleted, but the attachment remains. It's gone from the database, but it wasn't disconnected at the hypervisor level. So we have some stale data paths. It happens very rarely, but you need to clean that up somehow. Another thing that happens is also sometimes a user tries to delete a VM that has a volume attached, but the volume was already deleted. And in that case, you have the NVMe device, which is still consumed by QEMU. It has no data paths, and QEMU will not be able to close its process because it still has some device that is not clean, let's say. So in that case, we also need to manually disconnect the device because it was deleted before. And only then the VM will be able to close itself and clean up. So these are the funny things. Okay, so we need to, one more thing. So we have our custom SDS, we have our stuff, we know how to connect it, we know how to use it. But we need to somehow transition into prod. We don't want to put like thousands of volumes at the beginning of the new storage. We want to put like 10 maybe of them, just to see if everything works fine. Unfortunately, this is possible with 2 features of OpenStack, of Cinder basically. It's a filter function and goodness function. And those are the 2 mechanisms that can control how many volumes are put on the backend, or maybe what kind of volumes. So you can say, my storage doesn't like small volumes, so let's just configure it to reject the small volume request. It's possible to do with filter function. And this is exactly what we did on our production. We added new backend to Cinder, which is connected to the new software-defined storage. We've set some special filter function and goodness function just to slowly put new volumes on the backend and see if nothing's wrong. Then we changed the goodness function and filter function to put more and more and more volumes, and that's it. That's how we gradually enable the backend. And with the filter function and goodness function, there's a funny Cinder logic. I've realized that after questioning my sanity for like 2 days. So you can put some binary logic into those 2 functions, but the evaluator, which is currently used in Cinder, doesn't like that very much. So for example, true and false is true. Yeah, so I still didn't, I hope I will manage to fix it in the upstream. I still didn't have time for that, but if you do something, some advanced formulas, please be aware that it's possible you will hit this. Okay, so 30 minutes. and I'm done. Thank you very much for your attention.